In this lesson, we're going to look at solving radical equations. So solving for a variable when the variable is underneath the radical. So the first thing we're going to look at with this is talking about the restrictions on that variable. And we've mentioned this before, but when we're talking about restrictions, we're talking about what values can the variable not take on. And with square roots, and that's mainly what we're going to be looking at with these solving of radical equations, square roots we know cannot be negatives. So the entire radicand, that expression underneath the radical sign, the square root sign, can't be negative, meaning that it has to be positive. So when we go to state that restriction, we take the entire thing, right? So in this case, the entire radicand, the expression underneath the radical, is 2x minus 1. And we're saying that that entire thing needs to be positive. And we represent something being positive by saying that it's greater than or equal to 0. So 2x minus 1 is greater than or equal to 0. And then we'll rearrange that expression so that we get x by itself. So we would add 1 to both sides. So we're saying that 2x is greater than or equal to 1. Divide both sides by 2. So x is greater than or equal to half. So we put a restriction on any solution we get for x, saying that after we solve this, whatever the value of x is, it needs to be bigger than a half in order to work out and give us a value that you can actually take the square root of. Okay, so now what we take a look at is solving the equation. And again, this is very similar to methods that we've seen before with solving equations where we're trying to isolate the variable. The only thing that's different is that our variable of x is underneath a square root symbol. So we have to undo that operation. And since it's underneath a square root, the undoing of that operation involves squaring. But again, the first thing you want to do is get the radical by itself. So the first thing we're going to do here is subtract 5 from both sides of the equation. And we're left with here on the left 2x, the square root of 2x minus 1 is equal to 7. Now, once you have isolated the radical, you are going to square both sides. So what we're doing here is we square this entire side of the equation and we square this entire side of the equation. Okay? So the square root of 2x minus 1 squared, the squared and the square root essentially cancel themselves out because they're inverse operations of each other, and you're just left with 2x minus 1 here, and 7 squared is 49, so we're left with 49 on the right. Then it's just a linear equation that we're solving, so we'll add 1 to both sides, and we get 2x is equal to 50, and then we'll divide both sides by 2 and get that x is equal to 25. And checking back, that does fit our restriction in that x is in fact bigger than 1/2. We can also go back and verify that this solution does in fact work by taking it and plugging it into the original equation that was given to us, right? So we'll take this 5 plus the square root of 2 times x, which in this case we solved to be 25, minus 1, and seeing does it in fact equal 12. And we'll just follow our BEDMAS, so we'll have to do what's underneath the square root first. So 2 times 25 is 50. And we'll do 50 minus 1, which is 49. And we see here that it's 5 plus the square root of 49, which is 7. Does it equal 12? And it does. So our verification is correct in solving our radical equation in this sense. Okay? So what sometimes happens with our radicals is we get these values called extraneous roots. And we've seen those a little bit with our rational equations where when we would solve them, we'd realize that the answer that we got was actually one of our non-permissible values. And had we plugged it back in, we would have been dividing by 0. So this sometimes happens with radical equations as well. When you end up solving it, when you go back and check, one of them just doesn't work out. And I'll show you an example of what's going to happen here. But again, every time you go to solve an equation, you want to get in the habit, just like with the rational equations where we stated our non-permissible values, here we want to get into the habit of stating our restrictions. So in this one, again, it's a square root. So our radicand, right, the expression underneath the square root needs to be positive. So our first restriction is that 5 minus n must be greater than or equal to 0. So we're trying to get n by itself here. So we can bring the 5 over by subtracting it. We're left with negative n is greater than or equal to negative 5. Now we have to divide by negative 1 to isolate n. But remember, when you divide by a negative and it's an inequality, it switches the sign of your inequality. Okay, so what we have here is that n is in fact less than or equal to 5. So whatever value we solve for n, it needs to be smaller than 5 in order for it to work. Okay, so let's now solve the equation. So again, what we have is n minus the square root of 5 minus n equals negative 7. So similar to what we did before, we are going to bring everything that's non-radical to one side of the equation, everything that is radical on the other. Because I like to have positive radicals, I'm actually going to add this root 5 minus n to both sides so that it's positive. And at the same time, I'm going to add 7 to both sides to bring the 7 over here. So what I'm left with is n plus 7 on the left and a positive root 5 minus n on the right. Okay? Now that I've isolated the radical, right, so there's just a single radical on one side, in order to get rid of that square root, I need to square both sides. So I would square this right side of the equation, but I'm also going to square the entire left side of the equation as well. Keep in mind that when you do this, you're not just squaring each individual term. You've bracketed the entire expression here, and then you're squaring it. So this is actually going to become n plus 7 times n plus 7, right? Equals, and then this square root cancels with this squared, equals 5 minus n. So what you end up getting here is it's going to end up being a quadratic, because you're going to have to expand this out, and it'll be n times n, which is n squared, n times 7, which is a positive 7n, 7 times n, which is another positive 7n, 7 times 7, which is a positive 49, and it equals 5 minus n. And just like we spent so much time with solving quadratics before, we are going to bring everything over to one side, set it equal to 0, and then we can either factor or use the quadratic formula to solve. So what we'll have here is n squared, and then this 7n plus 7n gives me 14n, and then I would add n to both sides, so that will give me a positive 15n. And then I take my constant of 49 and subtract 5 here, so that gives me a positive 44 is equal to 0. So now that it's equal to 0, I can either quadratic formula or I can factor this. This actually does factor because 11 times 4 gives me 44 and 11 plus 4 gives me 15. So n plus 11 and n plus 4 are my factors, which means that n either equals negative 11 or n is equal to negative 4. Now, on first glance, just taking a look at the restriction, both of these values of n do fit the restriction. Negative 11 is in fact less than 5. Negative 4 is in fact less than 5 as well. So what we need to do to identify this extraneous root is actually plug it in and verify. Okay? And we'll create a new page to do that. So our original equation again, so what we're going to do here is do a verification. And the original equation was n minus root 5 minus n is equal to negative 7. So we're going to start with one of our options, which was n was equal to negative 11. So we're going to plug negative 11 in everywhere we see an n in the original equation, and we're going to check to see if that works out for us. So negative 11 minus 5 minus negative 11, square root of that, equals negative 7. Let's see if it works out. So we get negative 11 minus the square root of 5 minus negative 11, which is like 5 plus 11, which is root 16. Does that equal negative 7? Well, square root of 16 is 4. And we see here that we actually get negative 15 is equal to 7, and that's not valid. Okay? So negative 11 would be considered our extraneous root in this scenario. Okay? Let's just go through and verify our negative 4 value. So here again, we're plugging negative 4 everywhere we see an n. So negative 4 minus the square root of 5 minus negative 4. Does it equal negative 7? Evaluate. Negative 4 minus the square root of 5 minus negative 4 is the same as 5 plus 4. So root 9 equals negative 7. And this is negative 4 minus 3. And we do, in fact, get negative 7 equals negative 7. So our solution is, in fact, n is equal to negative 4. Okay? And n equals negative 11 is what we call an extraneous root. Okay? Where this is coming from is because when we square root numbers, we've often said, well, the square root could be positive or negative. But when we're dealing with radicals, it's only ever positive. So if we look back over here in this section where it was like the negative 11 minus the square root of 16, if you were to think about that option being, well, the square root of 16 is negative 4, and then we did negative 11 minus negative 4, it'd be like negative 11 plus 4, and that would give me my negative 7. But when you're doing these verifications, we don't think like that. We only think about the positive value that we get out of the radical, and that's where these extraneous roots come into play. Okay? All right, So now let's take a look at an equation in which we actually have two different radicals that we have to deal with. Okay? So what we have is they've already given me the restriction. So basically what's happened here is they've looked at both radicals and said, well, one radical is root 3x, which would imply that 3x has to be bigger than 0, which would imply that x has to be bigger than 0 as one of our restrictions. We would then separately look at the other radical and say, okay, well, that implies that the radicand there of 5x plus 4 needs to be positive, right, which implies that 5x must be greater than or equal to negative 4, which implies that x must be greater than or equal to negative 4/5. But because they're part of the same equation, both of these radicals, or both of these restrictions need to be true. So which one kind of encompasses both of them? And it's the x is greater than 0 one, right? Because if you're bigger than 0, you're obviously going to fit this restriction here of being bigger than negative 4/5. So that's why that restriction is there, is just x is greater than 0, because the other one is taken care of by that same one. Okay, we're going to try and solve this. So here's our equation. 7 plus the square root of 3x is equal to the square root of 5x plus 4 plus 5. Okay, well, we have a couple options. You could square this right away, and you'd have a binomial and a binomial that would need to be squared, or you could try and combine as many like terms as you possibly could. So I would probably start with subtracting 5 from both sides here, at least combine my constants, and what I'm left with is 2 plus root 3x is equal to the square root of 5x plus 4. Now in previous examples, when there was only one radical, we had talked about just isolating the radical. Once you get the radical by itself, you can go ahead and square both sides. That's impossible in this scenario because the radicands are different here. I can't even combine them into a single radical, so I can't just combine them into one. So what I can do at this stage is I can now go about squaring both sides. So I would square the left-hand side of the equation and the right-hand side. So in doing this, this is where we're going to use that property of multiplying radicals. And I have 2 plus root 3x times 2 plus root 3x on the left. And this square root and squared cancel out, giving me with just 5x plus 4. So I've done part of the job, and it's at least eliminated the radical there on the right. Now I'm going to actually expand this out. So 2 times 2 is 4. 2 times root 3x is 2 root 3x. Root 3x times 2 is another 2 root 3x. And root 3x times root 3x just gives me 3x. And all of that is equal to that 5x plus 4. The beauty of this is that, yes, there are still radicals, but at least these radicals are like radicals that can be combined. Because 2 root 3x plus 2 root 3x, because the index is the same, they're both square roots, and the radicands are the same, they're both 3x, these can be combined into a nice 4 root 3x. And we can just leave that there on the left-hand side and bring everything else over to the right. And we can say, okay, 5x minus 3x will just give me 2x, and 4 minus 4 is actually just going to be 0. So now what we have is 4 root 3x is equal to 2x. And now we can square both sides again. Okay, so we can again square the left and square the right. So squaring that, again, it means multiplying it by itself. So 4 root 3x times 4 root 3x is equal to 2x times 2x, right? We can expand it all out this way. And then we're multiplying whole numbers, so 4 times 4 is 16, and multiplying radicals, 3x times 3x would be 9x squared, but then that would just simplify into 3x. And 2x times 2x is 4x squared. So now what we have is 16 times 3x, that gives me 48x. So we have 48x here is equal to 4x squared here. And once again, we'll bring everything over, set it equal to 0. So 0 is equal to 4x squared minus 48x. We can factor out a 4x here. So 0 is equal to 4x times x minus 12, which means that x is either equal to 0 from this 4x term, or x is equal to a positive 12. Okay? But again, we need to check for any extraneous solutions, right? The question's even asked us to do that. It has asked us to check our solution. So we'll need to check both of those, 0 and 12. So again, we write down the original equation. So 7 plus root 3x, is it equal to square root of 5x plus 4 plus 5. Right, so one of our options was x being 0, so let's plug in 0 everywhere we see an x. So 7 plus the square root of 3 times 0 equals the square root of 5 times 0 plus 4 plus 5. So 3 times 0 is 0. 7 plus the square root of 0. The square root of 0 is just 0, so all that's going to be 7. Over on this right-hand side, 5 times 0 is 0. 0 plus 4 is 4. And root 4 is 2. And 2 plus 5 is, in fact, 7. So 0 is a valid solution. Our other solution that we need to verify was x equals 12. So again, we plug in 12 everywhere we see an x. So 7 plus the square root of 3 times 12 equals the square root of 5 times 12 plus 4 plus 5. So 3 times 12 is 36, so it's 7 plus root 36. 5 times 12 is 60. 60 plus 4 is 64. So that's root 64 plus 5. Root 36 is 6. 7 plus 6 is 13. Root 64 is 8. And 8 plus 5 is also 13. So both of our solutions of x equals 0 and x equals 12 are valid in this case. There are no extraneous roots. All right, let's take this now to some word problems. All right, so oftentimes there are situations in which squared or radicals are used in relationships between variables, and you need to be able to work with those types of relationships and work with squares and work with radicals in order to solve these equations. So let's take a look at this one. So what is the speed in meters per second of a 0.4 kilogram football that has 28.8 joules of kinetic energy? Use the kinetic energy formula, where EK is equal to half mv squared, where EK is the kinetic energy in joules, m represents mass in kilograms, and v represents speed in meters per second. Okay, so this is very similar to like a physics problem you might see, where you've been given all the variables, you just now need to plug them into the right spot, rearrange, and solve. So we've been given here the formula to use, so EK is equal to 1/2 is equal to 1/2 mv squared. Right? We've been given a 4 kilogram football, so we've been told that the mass is equal to 0.4 kilograms. We've been given that it has 28.8 joules of kinetic energy, so that EK is 28.8 joules. And we're being asked for the speed, so we're being asked to find V. So we just need to plug those values in. So what we have is 28.8 is equal to 1/2 times the mass, which is 0.4, times V squared. And we're essentially solving for V. And I know some of you might be saying, oh, we need to include the units. We're okay in this class right now because we're not really looking at the difference in the conversion between joules per kilogram and how that relates to meters per second. So right now we're just looking at a formula that's been given and each of the units have been told to us. Okay? So here what we have is we're going to try and solve this as best as we can. So we have 28.8 equals 1/2 times 0.4 will be 0.2 V squared. We will then divide both sides by 0.2. So 28.8 divided by 0.2 is 144, which is equal to V squared. Okay? And then we square root that. So that means that the velocity is equal to a square root of 144, which is 12. Okay? Now again, when we square root something, there are positive and there are negative answers. There's positive 12, right? Or there's negative 12. And since velocity does have magnitude and direction, you could consider that this could be, the velocity could either be 12 meters per second going forwards or 12 meters per second in the negative direction, right? So it could be negative. But since the question has asked us about speed, right, we know that speed is always positive. So really, we know that the velocity is positive, which we'll actually not call velocity anymore. We'll actually call it speed, right? Because we're now talking speed. So the speed of this football is 12 meters per second. And they've given us those units to use. Okay, so we're just again rearranging and solving an equation that does involve radicals because we have to isolate the variable by square rooting something. All right, let's look at a slightly different one where the radical is in the equation. So the mass, m in kilograms, that a beam with a fixed width and length can support is related to its thickness, t, in centimeters. The formula is t is equal to 1/5 times the square root of m over 3, where m has to be greater than 0, which makes sense because it's under our square root, so it needs to be positive. Also, the mass would obviously need to be something if it has a certain thickness. Okay? If a beam is 4 centimeters thick, what mass can it support? Okay? So we are given a value of the thickness, so we're given a value of t here as 4 centimeters, so I can plug that in for t here as 4 is equal to 1/5 times the square root of m, which is what I've been asked to find, is the mass. So again, what we're going to try and do here is isolate the radical, and we can do that by dividing both sides by 1/5. Dividing by 1/5 is the same as multiplying by 5, so what we get is 20 is equal to the square root of m over 3. Now we can square both sides here, and 20 squared is 400, which now equals m over 3, and multiply both sides by 3 to get m by itself, and what we get is 1200 equals m. So the beam can support a mass of 1200 kilograms when it has a thickness of 4 centimeters. Okay, I'm just relating them all together. All right, so those are all your examples. So some with context, some without context, some with extraneous roots where you do need to verify, but you need to verify all of your solutions now that you know extraneous roots are always possible. Sometimes they are there, sometimes they're not, but there is always the possibility. And these are your practice questions to attempt.